Buenos días, estudiantes de Álgebra 2, or buenas tardes, or buenas noches, depending on what time you're watching this video. I know some of you guys like to stay up late and do math homework. So, last class, or last video, we talked about imaginary numbers. So let's just review imaginary numbers very quickly. An imaginary number, well, a pure imaginary number is one of the form bi. Remember, we call this pure imaginary. And b is a real number. And we said I represents the square root of -1. We also said that I squared, by definition, equals what? -1. A pure imaginary number, for example, square root of -25, is not a pure imaginary number. It needs to be rewritten as I times the square root of 25. Now it is a pure imaginary number. So when we're working our problems today, I always want you guys to take a square root of a negative and rewrite it as a pure imaginary number first. This then would become 5i, which is also a pure imaginary number. Remember, a pure imaginary number has its real part and then I. The real number times I. Okay, so it's just a quick review from last class. So today we're talking about complex numbers. Well, what are complex numbers? Complex numbers are simply combining a real number with a pure imaginary number. We're going to draw a little tree here to kind of show you guys, illustrate how these all connect. So a complex number is of the form a plus bi. A is a real number. Real number. And b is a real number. I, what does I represent? I is the square root of -1. So these are complex numbers. Now, complex numbers are kind of an umbrella for other sets of numbers that we've already talked about. So I'm going to put this in a box here. These are our complex numbers, a plus bi. And just very quickly, an example I'll put over here would be something easy like 3 plus 2i. Okay, that's a complex number. Now, coming off of the complex numbers, let's do this. We've got imaginary numbers, regular imaginary numbers. Now, imaginary numbers, let's do this in purple. Okay, imaginary numbers are basically the same thing as complex numbers. A complex number is imaginary, okay? Except for here, b cannot equal 0. We have to have the imaginary part here, the I. Otherwise, it's not imaginary anymore. We only have the real part, and then it becomes a real number. Move this. Okay. So we've got our imaginary numbers, which are basically the same as complex numbers, except here, b cannot equal 0. Now, off of imaginary numbers, we have what we've already talked about, our pure imaginary numbers. I can make this smaller here. Yes. Oops. No, it doesn't want to do it. right, anyways, so now we've got pure imaginary numbers. And a pure imaginary number is what we already talked about last class. It's of the form bi. And again, b is a real number. So that goes for this too. A is a real number, b is a real number. Here on the bottom, b is a real number. And b cannot equal 0 here, because otherwise it would just become 0. We don't have our imaginary number anymore. Now, off to the left, over here, we have the real numbers. So to the right, we've got imaginary, and to the left, we've got real. Together, the real and the imaginary create the complex numbers. So real numbers, you can think of as a plus bi, but without the bi part. Here, b equals 0, always. So you don't have this. It's just really a that we're talking about. So these are our real numbers. Now, off of the real numbers, we have rational and irrational numbers. Rational. So a rational number, remember, is a number that can be made into a fraction. It doesn't have the imaginary part. And an irrational number is a number that can't be made into a fraction, like pi or square root of 5, square root of 2 is also irrational. So these are examples of irrational numbers. Rational numbers are things like 0.33 repeated, because that's 1/3. You can make it into a fraction. 5/7, that's rational. 6, that's rational. So rationals and then irrationals. So these are number sets that we've discussed. Complex numbers are made up of real and imaginary, so a plus bi. So this is just an image, a visual to get you guys understanding how everything connects. So let's talk a little bit more about complex numbers. Complex numbers are actually pretty easy to work with because it's just like adding and subtracting like terms and multiplying square roots. So let's first look at adding and subtracting. So an example of adding would be one like 3 plus 6i plus 4 minus 2i. Now if this was a minus inside here, I would distribute into the second parentheses, but it's a plus, so I can just drop the parentheses and combine my like terms. Well, my like terms are the real parts, and then these imaginary parts, the pure imaginary parts. So 4 plus 3 is 7, 6i minus 2i, well that's 4i, and you're done. Easy peasy. Let's look at another example, this time with subtracting. 3 plus 6i minus 4 minus 2i. Now here we have a minus sign in the middle that needs to be distributed into the second parentheses. So we get 3 plus 6i minus 4 plus 2i. Don't forget a negative times a negative is a positive. And now we're going to combine our like terms. 3 minus 4 is -1. 6i plus 2i is 8i. And that's it. That's how easy adding and subtracting are. So let's look at multiplying. Okay, an example for multiplying. 3 plus 4i times 5 plus 2i. So here we're just double distributing. 3 times 5 is 15. 3 times 2i is 6i. 4i times 5 is 20i. And 4i times 2i is 8i squared. Now we're going to combine our like terms. And at the same time, I want you to be very careful of this. What does I squared equal? Well, remember from last notes that I squared is the same thing as -1, right? I is the square root of -1. When you square it, you get -1. So I'm going to rewrite this as 15 plus 26i, because 6i plus 20i are like terms, plus, instead of 8 times I squared, now I have 8 times what? Well, 8 times -1. So that gives me 15 plus 26i minus 8, and then 15 minus 8 is 7. So we get 7 plus 26i. That's your final answer there. Okay, there's your complex number. So that's all you're doing when you're multiplying. Now, dividing. Dividing, and when you divide, just like we don't leave a radical in the denominator, you normally don't see an imaginary number, an I, in the denominator. So we're going to multiply and we're going to remove I from the denominator. And so here's an example. Let's say you have 5 minus I divided by 2 plus 3i. Now think about when we tried to get a square root out of the denominator when we had a binomial. You couldn't just multiply by I in the numerator and denominator. You couldn't just multiply by square root in the numerator and denominator. You had to multiply by the complex or the conjugate. So here we're going to do the same. We're going to multiply by the conjugate. We call this the complex conjugate. And all you do is change the sign in the middle. 2 minus 3i over 2 minus 3i. So all we've done is change this plus to a minus. Okay, and notice that we did that in the numerator and denominator. That's like our clever form of 1. And now I'm just going to double distribute everything. So 5 times 2, 10, 5 times -3i, -15i, -i times 2, -2i, -i times -3i is positive 3i squared. All over 4 minus 6i plus 6i minus 9i squared. Now be careful of your I squareds. What does I squared equal? I squared equals -1. So we're going to combine our like terms, and I get 10 minus 17i plus 3 times, instead of 3 times I squared, I have 3 times -1, all over 4. Notice the minus 6i and the plus 6i cancel. That's the whole point in doing the conjugate, so that we can get the I out of the denominator. And then minus 9 times, instead of I squared, we've got 9 times -1. And I'm almost done. So 10 minus 17i minus 3 over 4 plus 9. -9 times -1 is positive 9. 10 minus 3 is 7, so we get 7 minus 17i over 9 plus 4 is 13. And you're done.